This video contains the solution for number 4 in the 2010 AP Calculus BC free response question, Form B, number 4. We have a very geometric looking graph. It makes me suspect that we will be taking area under that curve at some point. This is a graph of velocity, which should make you think also that it's a graph of a derivative. It's the graph of the derivative of position. So that's, let's see, they're going to do a distance function as well, consistent with their notation. We could write that like that to remind ourselves that it's a derivative. So a squirrel starts at time 0 at building A, travels along a straight line with this velocity, and piecewise linear, so those look like straight lines, and they are. So for A, at what times in this interval, if any, does the squirrel change direction? This is a graph of velocity, and we know that changing direction means going from having positive velocity to negative velocity, or vice versa, having negative velocity to positive velocity. So here's some positive velocity, here's some negative, and here's some positive. So we are changing direction here and here. That looks like it's at 9 and 15. So for A at t equals 9 and t equals 15, because velocity changes its sign. You could write that it goes from positive to negative, or negative to positive, or whatever you like. So, part B. At what time in this interval is the squirrel farthest from building A? How far from building A is the squirrel at that time? Well, I think we need to think about area now. The squirrel's moving forward here, and then moving backward, and then moving forward again. So, since this is positive velocity, this is the rate, and this is negative velocity, this would be a maximum of the squirrel's direction, of position, excuse me, because we have increasing and then decreasing, and then we have decreasing and increasing. This would be a relative minimum. And I think by looking at the areas, if the squirrel starts at the building, this is a big amount forward compared to this relatively smaller amount back. And then we go forward again, but not nearly enough to get back to here, right? That looks like about half the area of this. So it looks like that is going to be the furthest that the squirrel gets away from the building. So that's t equals 9. And then how far away is the squirrel at that time? Well, the squirrel's at 0 here, and if we wanted to know how far the squirrel went, this is a rate, so the area under this tells us the amount of change of the original position function. So let's start finding our areas here. This is a 2 by 20 triangle. 2 times 20 is 40. 1/2 base times height. So it's 20 there. This is a, let's see, 1, 2, 3, 4, 5 by 20 rectangle. That's 100. This triangle is exactly the same as that one, and area-wise anyway. And this, we have a 1 by 10 triangle. Half that is 5. And why am I finding this area? We're going to have to find all the area in a minute, so I might as well finish the job. 1, 2, 3, 4 by 10, that's 40. That's another 5, same as that one. And let's see, that's another one of those 5s. And that is a 2 by 10, that's 20. So that was, in fact, half of that. Okay, so when we're here, looks like the squirrel's gone 140 units. I guess they didn't give us any units, did they? So 140 units from building A. And just a note there, It was just 140 because the squirrel started at building A. In other words, the squirrel's initial position was 0. If it had been something else, then we would have had to add that to the 140. But since the squirrel started at 0, the 140 displacement is where we are. That's actually the position 2. It's 140 plus the 0 where we started. All right, part C, find the total distance the squirrel travels during the whole thing. Well, we pretty much have that, right? Total distance traveled, remember, as the integral, in this case it would be from 0 to 18, the absolute value of the velocity function. So that means we want to keep all of our areas positive. If we wanted to do displacement, then this would be negative, but we want total distance. So that's 140 plus 50 plus 25. So let's see, 140 plus 50 plus 25 is 215 units. And part D, write expressions for the squirrel's acceleration, velocity, and distance from building A that are valid for this part of the graph. Well, since this is the velocity graph, why don't we start from that? If this is a piecewise function, so we just need to write the equation for this piece. So let's see, it goes through the point 7, 20, and 10, negative 10. So velocity function goes through 7, 20, and 10, negative 10. So I need to find the equation for the line, and that will be that piece of the velocity function. So slope is negative 10 minus 20 over 10 minus 7. Negative slope, that looks right. And so let's see, that's the slope. I can use either one of these points. So let's use this one. So y equals mx plus b. So b, I'm going to add the 100 over to here. B is equal to 90. So the velocity function, or in other words, the equation for this line, good from 7 to 10, is equal to minus 10 t plus 90. And that looks about right. It's downward sloping, and if we extend it this way, I have a y-intercept somewhere up there at 90. So there's a velocity function. Well, acceleration's easy from there. Acceleration is the slope or derivative of this. So that's negative 10. The trickier one is position. So we're done with this. Done with that. But position is the antiderivative of this. So the antiderivative of negative 10t is negative 5t squared plus 90t plus c. And the tricky thing here is that you can't just use any initial value, like this one, for example, because that's not part of this line, right? We can only use stuff from the interval from 7 to 10, including the endpoints. So we need to figure out somewhere, there are different things that we could use. We already know that at time 9, the position is 140. You could also use at time 7, that area would be 120. You could use that also. I'm going to go ahead and use the one that we already have from earlier on. I know that at time 9, the position is 140. And I'll use that to solve for C. So the position is 140 when time is 9. And this is no calculator. It's kind of mean of them. And Let's see. So let's see if we can manage this horrible arithmetic without our calculators. 9 squared is 81. 5 times 80 would be 400 plus the extra 5 would be negative 405, I believe. And then 90 times 9 times 9 is 81, so that would be 810 plus C. So let's see, well, that looks like negative 405 plus 810, that's 140 is equal to 405 plus C. And then subtracting that over there would give me that C is equal to, let's see, 265 negative. So my position function is x of t is equal to negative 5t squared plus 90t minus 265. And, you know, in the grand scheme of things, that was the hardest bit there. That's probably worth 1 point out of the 9. So the first time I made this video, I confess, I used the initial value 0, 0, not thinking about the fact that that's not part of this line, right? So it would not be valid for figuring out the acceleration, velocity, and position that work in this range. And it gave me it gave me a C of 0. The math was easier, but I got the wrong number there. So only 8 out of 9 for me on that one the first time. This is the correct answer.